Welcome to the massive open online course on Aspen Plus. In today's lecture, I shall discuss about some practice problems which are miscellaneous in nature. Unlike the last two lectures when we have discussed about the binary mixture or pure components, in this lecture, we shall talk about some miscellaneous problem, 4 in numbers, and then we shall perform 2 case studies in detail. The first practice problem that we will do is about obtaining the activity coefficient graphs for binary mixture of nitroethane and cycloheptane. And we shall use ideal method, inertial method, and uniquark property method and analyze the situation. Whatever happens by using these methods, we will see and analyze. Let us go to the Aspen simulation window. So here we have to add the components. The first component is nitroethane. So we have to find nitroethane. This is the one, we add it. And the second component is cycloheptane. This is the one. Okay. So we rename it as nitroeth and cyclohep. Now press next. So we shall use 3 property methods: ideal, inertial, and uniquark. So first one is ideal, then inertial, and uniquark. So the 3 methods we run. Okay. Now we have to look for the activity coefficient graph of the binary mixture. So let us bring in the binaries tool. Here we have to begin with TXY. First, let us choose ideal and then run analysis. We have assumed it an ideal system, so the graph looks like that of an ideal system. So anyway, we are not interested with the TXY plot. We have to look for the activity coefficient plot. Now, as we know, the activity coefficient of an ideal system is always 1. So we expect that we will get a curve of unity, and that's what we get here. So the value of activity coefficient is 1 at any mole fraction of nitroethane or cycloheptane. Next, we shall take the inertial property method in the calculation option. So just press inertial and redo the binary analysis. Again, we obtain the TXY plot, and this is strange. It looks like it is as good as an ideal plot. So anyway, let us see how the activity coefficient looks like. And yes, the activity coefficient, again, it is saying it is 1. So even inertial system, it is suggesting that the activity coefficient is 1. That means it is identical to an ideal condition. But it is strange, inertial should not give this kind of result. Let us see what uniquark property method suggests. So let us take uniquark and redo the binary analysis. Here we get slight difference from the ideal system, or for that matter inertial system. Now let us check the activity coefficient curve. Yeah, now we are getting some different nature. Obviously it is not much. The activity coefficient is coming down from 1 to 0.943. So the difference is not much. Okay, so the scale of y-axis is very narrow, as if activity coefficient doesn't change with the mole fraction of nitroethane. Anyway, at least we are getting some change from ideality. But we are concerned why inertial method is not giving any change of activity coefficient. For that, let us go back to our inertial method and check their parameters, the binary parameters of inertial method. And here we find the binary parameters of inertial method, and we are surprised to know that none of the binary parameters have been calculated. Aij, Aji, Bij, Bji through Eij and Fij, Fji, nothing has been calculated. And that is the reason it is showing the result as good as the ideal method. It doesn't mean that inertial method is equivalent to ideal method. Okay, so what we shall do, we shall take this estimate using UniFAC. So the moment we do it and we run, then all the missing parameters, at least the maximum parameters of inertial, are being computed through UniFAC. Now we go back to our binary input. Calculation option, inertial, and see the analysis once again. And yes, now the TXY diagram is different from ideal property diagram. That means now inertial has calculated it properly. Anyway, let us not bother about TXY diagram. We go to activity coefficient diagram and we find activity coefficients changing with mole fraction of nitroethane. And that's what is expected. For inertial property method, this kind of graph is expected. So it is decreasing from 8 to 1, and liquid cycloheptane, and activity coefficient increases from 1 to 4.6 with increase in the mole fraction of nitroethane. And this result corresponds to 1 atmosphere pressure. If we increase the pressure, this figure will also change. Now let us go to the second practice problem that we have. It is about considering the ternary mixture. So we add the third component with the system that we just talked about, that is nitroethane and cycloheptane. We add the third component, that is ethanol, so it becomes ternary mixture. Now we have to use Aspen distillation synthesis feature for detecting azeotropes, and we have to generate a report. And here we will use the NRTL property method. So for that, let us go back to the Aspen simulation window once again. So here, add those components: nitroethane, add it, then cycloheptane, add it, and finally we take ethanol. So just rename it. Press next. Take NRTL method. Run. Okay, so this time we won't do that mistake. We shall go to the binary parameters, choose NRTL, and we'll say estimate using UniFac, and we will run it once again. So it has run. It has estimated all missing parameters with UniFac. Now we shall go to the ternary diagram. So let us bring the ternary diagram tool. Here a dialog box appears. The dialog box is distillation synthesis. So exactly that's what we are asked to do. Use Aspen distillation synthesis feature for detecting azeotropes and generating report. So every time you press the ternary diagram button, this dialog box appear. Usually we choose this particular button because we continue to do the Aspen Plus ternary diagram, but it has other features also. You can learn more about Aspen distillation synthesis by pressing this button, or you can find the azeotropes by pressing this button, and you can use distillation synthesis ternary map by pressing this button. In this exercise, we will use this third button, that is use distillation synthesis ternary maps. So we press it, and then we get this particular distillation synthesis, and here we have several information. So the component list has been given. So component 1 is nitroethane, cycloheptane is component 2, and ethanol is component 3. And the analysis is done at pressure, which is 1 atmosphere. The VLE, LLE, the model is NRTL, and basis is mole fraction, not mass fraction, and temperature is calculated in centigrade unit. So they will calculate residue curve, azeotrope, and distillation boundary. Now we have ticked all of them because we want them to calculate all of them. In case you do not want to see the residue curve, you can untick this, or if you do not want either of them, you can untick this. So that is up to your convenience. And the left hand side, you will find this explorer where you can get the output in pure component form or azeotropes, singular points. You can generate a report and you can see the ternary plot. Now let us go to the pure component first. Let us see what they are. So it says stable node. So pure component stable node is actually they are the boiling points of nitroethane, cycloheptane and ethanol respectively. If you want to check, you can check here. Just go to internet and write nitroethane. And you can see the boiling point is 114 degrees centigrade. So it is 114 degrees centigrade. Similarly, cycloheptane you will find 118.8. It is 118 point, well, it has calculated as 1. Probably this is the experimentally found one. And it has been calculated through inertial method. So that kind of difference may be observed. And ethanol, it is 78.31. Let us see what internet says. Ethanol, it is 78.37. 78.31. So stable node is the boiling point of these liquids at 1 atmosphere. Mind that we have calculated it as 1 atmosphere. If you change this value, then output will also change. If you change it to 2 atmosphere or 3 atmosphere or some other pressure, then the stable node, the values will change, the boiling point will change, that information will change. Azeotropes. There are 4 azeotropes you get. 3 are binary azeotropes. You will find the binary azeotropes over here. So this is the first one is the binary azeotrope. It's an azeotrope between nitroethane and cycloheptane. The third one is a binary azeotrope between nitroethane and ethanol. And the last one is a binary azeotrope between cycloheptane and ethanol. All these 3, we have one of the components missing. So they are binary azeotropes. We have only one azeotrope over here, that is ternary azeotrope, which is at 75.7589 degrees centigrade. And obviously this is unstable node. And these are saddle node because if you see the ternary plot and residue diagram, you will see why it is called saddle point or saddle node. And similarly, you can see the singular point. Singular point is nothing but the collection of all stable nodes, saddle nodes, and the unstable nodes. So it is collection of all the boiling points and the azeotropes. And finally, the report. If you press report, then nicely generated azeotrope search report will be given. You will find here the mixture investigated for azeotropes at pressure 1 atmosphere, the component ID, component name, classification, the temperature, everything will be given. There are 4 azeotropes. You will find all those 4 azeotropes over here, their temperature, and finally, this is the ternary plot. So in ternary plot, this one is the ternary azeotrope. This is a mixture of 3 points. And these are the 3 binary azeotropes. And these are the stable nodes along with the boiling point. So this information is given. Cycloheptane 100% with boiling point. This node is 100% nitroethane with this boiling point, and this node is 100% ethanol with this boiling point. And the mole basis information will be available when you hover this mouse on the graph. It will tell about corresponding mole fractions or compositions of the ternary mixture. So that is how we use the Aspen distillation synthesis feature for detecting azeotropes and to generate report. Now our next problem is examining whether nitrogen, oxygen and argon gas may be separated through cryogenic distillation. Cryogenic distillation means the distillation that is done below 0 degrees centigrade. Now, at normal temperature, all these components like nitrogen, oxygen, or argon, all of them are gas. So their boiling points are much below 0 degrees centigrade. So we have to see whether they can be separated through cryogenic distillation. And we will examine it using the residue curve. And for that, we shall use ideal gas method, inertial method, and SRK model for property analysis. So for that, let us open the Aspen simulation window. So write the components: nitrogen, oxygen, and argon. Press next. And we have 3 methods: ideal, NRK, and SRK. Ideal, inertial, SRK. Run the property methods. Run them twice or thrice, as many as times it wants. Okay. Now they are done. There is a error. I know what is the error. Actually, when you are using SRK method, then you have to use free water method as steam NBS. And that's exactly what the run status should say. Let us check. Yes, free water method should be steam NBS when main property method is SRK. So that's a common mistake people do. So we have to check it with steam NBS. And run. Yeah, now the run status is okay. Now we have to bring the residue curve. Nitrogen, oxygen, argon. First the property method, ideal. Okay. So this is with ideal curve. Let us bring another residue curve. Let us use inertial. Okay. And let us bring the third residue curve. and that is using SRK. Okay, so now basically we have three residue curves. The first one, it has been generated using ideal property method. The second one has been generated through inertial method, and third one has been generated through Redlich-Kwang's wave method. And we find none of them are showing any kind of azeotropes. Okay, so only the experimental investigation will tell you which method will be most ideal for this kind of situation. But why we have tried three methods? Because the first one is ideal method, the second one is inertial, so it is activity coefficient based model, and the third one is Redlich-Kwang's wave model. This is equation of state based model. So all three types of modeling technique we have tried, and none of them are showing any sign of any kind of azeotropes. So the answer to the question which has been asked, examine whether this gas may be separated through cryogenic distillation, the answer is yes. It is possible to separate them through cryogenic distillation. And then the final practice problem that we have, it is about observing the liquid-liquid equilibrium diagram of water trichloroethane binary system using Wilson property method. So for that, let us again go to the Aspen simulation window and open a new simulation. Okay, so we enter water, then trichloroethane, okay, we choose the first one. So we have to rename it as TRC. Press next. We'll use Wilson method, and we shall estimate using UNIFAC. Otherwise, these particular parameters are not being calculated, so run them. Now we have to see the liquid-liquid equilibrium diagram, and let us say binary. Water TRC at 1 atmosphere pressure, Wilson method, run analysis. Okay, so this is the diagram that we have, and if you check the VLE, Y versus X, and you will find like this. So basically this is a liquid-liquid diagram. Basically water and trichloroethane, they do not mix with each other. They have poor solubility. Now we will perform two case studies. They will be a bit detailed and we will see more information in this. The liquid-liquid equilibrium that we have just seen, the same problem will be extended in the first case study. Here, acetone needs to be separated from equimolar aqueous solution. That means we have a solution where we have water and acetone, and they are equimolar 50-50. And we have to use trichloroethane to extract. So as we know, water and trichloroethane, they are not miscible at all, that we have seen in the previous practice problem. So we expect that TRC, when we mix with this water acetone mixture, then TRC will take out the acetone from here. So it will extract the acetone from that mixture, because acetone mixes with water, acetone mixes with TRC. But water and TRC, they do not mix with each other. So this can be used for extraction. We will use the flash 3 model for extraction, because we know flash component, it has vapor and liquid, but flash 3, it is vapor, liquid, liquid. So there are 2 liquid outputs we have in flash 3 model, so we can use it for extraction. We will use NRTL property method, and the nominal operating condition is 25 degrees centigrade and 1 atmosphere pressure. So it is normal operating condition. Now 2 questions have been asked. Does it help in recovery if you increase the temperature, or if you employ 2 extractors in series? That means one flash 3 which is in series with another flash 3. That means the output of this will be added into this. So whether this kind of system will help to get more recovery of acetone. Now we have to analyze this using the ternary diagram, and we have to explain. So for that, let us go to our Aspen simulation window. We won't open the new simulation window, we will use this one only, because we have to just add one component, that is acetone. So we already have water and TRC, so we add acetone, and we shall use NRTL method. Now we have to analyze with ternary diagram to explain. We will do it later. First, let us see what happens for this kind of system. Let us simulate the system first. So let us go to the simulation window. Bring the flash 3. So add the material first. So this is the feed, this is vapor, this is liquid 1, and this is liquid 2. So this one we have to reconnect source, this one. So this is feed, this one is vapor. Well, actually we won't get any vapor in this, because at normal temperature and pressure condition, none of this water, TRC and acetone, none of them have any vapor phase. But Aspen has to have some line with it. Obviously it will go dry after the simulation, doesn't matter, but we have to set this line, vapor line. And here we have to press liquid 1, and this is liquid 2. We will use V instead of vapor. Okay, so press next. It is 25 degrees centigrade and 1 atmosphere pressure. And it's an equimolar mixture of water and acetone. So it is water and acetone, equimolar. And in the flow sheet, we have to have a second stream, that is TRC stream. So we add in the second stream over here, and that we call TRC stream, where you have only TRC of 1. One atmosphere, that's it. So press next. Okay, so the flash tank, let us run it at 25 degrees centigrade and the same pressure 1 bar. Okay, so now it is ready to run. Let us revisit the main flow sheet. We have a feed which is equimolar, 1 kilomole per hour of water and 1 kilomole per hour of acetone. So it's an equimolar mixture. And we are sending 1 kilomole per hour TRC into it. It is flashed. Vapor will go dry because it is at normal temperature and pressure. We will get 2 lines of liquid, liquid 1 and liquid 2, because one will get the extract, the another will get the raffinate. So now let us run. Okay, so we have run the simulation. Go to the stream result, and this is the stream result that we have. See the molar flow rate. We have, out of 1 kilomole per hour, we have got 0.87652 kilomole per hour in the L1. TRC is very small, and we have got 11% or 0.1122 kilomole per hour acetone over here in the raffinate phase. In the extract, we will have almost entire TRC, and we will have 88% of acetone going to the extract phase. Okay, so let us write this information. So we have to remember this information, this information, this information, and also this information. And we also have to remember the amount of heat duty. Let us use it in SI unit. So it is nearly 1 kilowatt, 1.073 kilowatt. This is the amount of heat duty that is required for running the system. Okay. Now we keep this information with us. Let us increase the temperature. So the first problem, if you increase the temperature, can you get a better result? For that, let us increase the temperature to 50 degrees centigrade. Suppose we increase the temperature from 25 degrees centigrade to 50 degrees centigrade. What happens? Let us run it once again. We see the heat duty in this case is 3.9257. So from 1 kilowatt, it is going to 3.9257 kilowatt, almost 4 times the energy requirement is there for an increase of temperature from 25 degrees centigrade to 50 degrees centigrade. Okay, but are we getting a better result? See the stream results. So these are the stream result we have in the mole flow rate. Check the mole flow rate. Here we are getting acetone 91%. So let us check. So here it is. Here it is 91.49% recovery of acetone by using 50 degrees centigrade. But what happened for the previous two cases? It was 88.7744% of acetone. So you are spending 4 times of energy just to increase it from 88.77 to 91.49. So only 3 or 4% increase, your energy requirement will be 4 times higher, which may not be advisable. Now, the second option, it is saying if you employ 2 extractors in series. For that, let us change our flow sheet a bit. So here we bring in another flash. So this is our second V. This is our L1, L2, and then this needs to be connected to this one, and we need another TRC over here. So this one we name it TRC2. This is V2, which again will go dry. Let us say this is L1 dash, and this is our L2 dash. Okay, and we will mix up 2 extracts together so that our calculation we do not have to do separately. So for that we connect this thing over here, and this one we reconnect destination to this. Okay, so we have 2 connections, 2 inputs and 2 outputs. Okay. Okay. And the total of extraction, it is this one. We write total. So we will check what is the composition of the total stream. And we will not send the entire 1 kilomole per hour over here. We will distribute it 0.5, 0.5. So we will distribute it. So let us say TRC is 0.5 and TRC2 It is again 25 degrees centigrade, 1 atmosphere pressure. And this is 0.5. And the blocks B1 we reduce to 25 degrees centigrade. We do not want any major change in pressure. Okay, temperature 25 and pressure 1 atmosphere. Okay. Now let us run. Okay. Now we have to check the stream result of B3 because it will give us the output total. Now you check what is the output in B3. Here we see the amount of acetone is 0.96. So 96%. So from from 88.77 to 96.54. So we have increased the extraction capability of the unit by adding another extractor in series. And what is the heater duty? So heat duty will be 308 watt and B1 712 watt. So 700 and 800, nearly 1.5 kilowatt. So earlier it was 1 kilowatt, now it is 1.5 kilowatt. By keeping two extractors in series, we are increasing the heat duty by 50%, but we are extending the purity of acetone from, or extraction of acetone from 88% to 96%. Now, obviously, to add an extra unit, you need a capital cost, but your recurring cost, that is heat duty, will be lower. So if you are given two options like this, then obviously this option is better. Now we have to analyze the situation using ternary diagram. Now, for that, we have to go back to the property method and check the ternary diagram. Run analysis. It is something like this. Let us increase the number of tie lines. So make it 15 tie lines. Yes. Now, initially it was equimolar, right? Because in the B1 mixture, it was 1 kilomole per hour of water, 1 kilomole per hour acetone, and 1 kilomole per hour TRC. I'm not talking about two extractors in series. I'm talking about the case where we were using single extractor. In that case, inside the extractor, it was truly an equimolar composition. Equimolar composition means the location of composition will be somewhere here, because here it is equimolar point. Now, if this is the equimolar point, then any kind of extraction will go one phase at this point and one phase at this point. Okay, so that's how the extraction works. Now you can check the composition of extract and raffinate phases. You will see them this point and this point. For instance, this is the point where water is very less, so it is the composition of L2. On the other hand, this is the composition of L1, where we'll have almost no TRC. TRC is almost 0, and it will be nearly 91 or 92% of water and very small amount of acetone. So let us see. So here almost no TRC, water is nearly 90%, and acetone is very, very small. So that's how you can analyze the ternary diagram and check whether your end result of simulation matches with whatever you examine through ternary diagram. Okay, so our second case study is about PT envelope and distillation. So it is about an equimolar mixture of water, cresol, methanol, and pentanol. We have to use Peng-Robinson method and study the PT envelope. Now, two questions are asked. First question is, what is the vapor fraction at operating condition, which is 245 degrees centigrade and 25 bar pressure? And what happens for a binary equimolar mixture of water and pentanol? That means that in the second condition, we will have only water and pentanol. There will be no cresol, there will be no methanol. At the same operating condition, that means the operating condition will still be 245 degrees centigrade and 25 bar pressure, but in absence of cresol and methanol. So this is the case study that we have to perform. For that, let us go back to our Aspen simulation window. Okay, so add water, cresol, methanol, and pentanol. Okay, press next, use Peng-Robinson, press next, okay, run. Okay. Now, the first task is study the PT envelope. So, let us bring in PT envelope. Now, let us take equimolar flow rate that has been asked. Equimolar mixture of water, cresol, methanol, and pentanol. So it is 1, 1, 1, and 1. And run analysis. So this is the PT envelope we have got. But we have only two lines. One is vapor fraction 1, that is the blue line. This is the dew point line, and vapor fraction 0, this is the bubble point line. But we may not be happy with only two lines. We need some more lines for analysis. For that, let us add additional vapor fraction line at say 0.2, 0.4, 0.6 and 0.8. So run the analysis once again. Yeah. So we have few more lines like this. So we just shift it over here. Yeah. So each and every line, the legend is also given, so you can check the legend and find out which line corresponds to what. Now, question is, what is the vapor fraction at operating condition 245 degrees centigrade and 25 bar pressure? So it is 25 bar pressure. So 25 bar pressure means this line. And 245 degrees centigrade means this line. So this is the point which we are looking for. Okay, so what vapor fraction it is? This is a gray line. So I think it is 0.4. Yeah. So this is 0.4 line. Okay. So our condition is over here. This is the point. Okay. That means if we run the distillation at 25 bar pressure and 245 degrees centigrade, then the 40% of the feed will go into the vapor phase. That's what it means. So let us cross check. Go to simulation and bring in the separator, flash, material in, this is vapor out, this is liquid out, this one we reconnect to destination. Okay, rename, this is my feed, this is my vapor, and this is liquid. Okay, next it will ask for input streams. So 245 degrees centigrade and 25 bar pressure, and all of them are 1 equimolar mixture of all of them. Press next. Okay, block again 245 degrees centigrade and 25 bar pressure. Run the simulation. Yes. So see the stream results. So molar flow, it is 4 kilomole per hour. But what is the vapor fraction? It is 1.5734. So 1.5734 by 4. So 1.5734 by 4, that is equal to 0.39335, which is nearly 0.4. And this information we have obtained from PT envelope. Okay. Now the next question is, what happens for binary equimolar mixture of water and pentanol at the same operating condition? That means we shall chuck out this cresol and methanol. Only water and pentanol will remain. It will be equimolar mixture. So for that, let us go to the feed input and we chuck out this cresol and methanol. Okay. And we run the process. See the results. And we find in the molar flow, we don't find anything in the liquid. Here we don't find anything in the liquid phase. Everything has gone to the vapor phase. Okay. So this is an interesting result, that if we chuck out cresol and methanol, then at the same operating condition, everything will go into the vapor phase. Nothing will remain in the liquid phase. Now let us cross-check this with the PT envelope. For that, let us go to the property analysis, the PT envelope. Here you delete this one, delete this one, and run the analysis once again. Now the curves are a bit different. Okay. So let us analyze this curve. Now, what is the condition? It is 245. So 245 is here, this line. And what is 25? 25 bar pressure, it is this line. So this is the point. Okay. Now check it very closely. This point where my mouse is hovering around, this is just outside the vapor fraction 1 curve. It is not within this. So actually, anything which is of this side, it will be completely vapor. Anything this side will be completely liquid. Only between these two vapor lines, vapor line 0 and vapor line 1, within this there will be a liquid and vapor mixture. Okay. So in this particular case, when we are driving cresol and methanol out of our system, then for the same operating condition, it is bringing the system into the completely vapor region. Okay. And as it is coming at the completely vapor region, we are not getting anything in the liquid. Now let us change the temperature from 245 degrees centigrade to 240 degrees centigrade. And let us check what happens. Mind that this is near the curve 0.8 vapor fraction. So if we change our temperature from 245 degrees centigrade to 240 degrees centigrade, keeping our pressure constant at 25 bar, then we were expected to have a vapor fraction of 80% nearly. Let us check that. So go to our simulation once again. Here in the feed, we make it 240 degrees centigrade, and the B1 also keep it 240 degrees centigrade and run the simulation once again. Okay, now see the stream results. Here you will find what is the vapor fraction. Vapor fraction is 1.62763. So the liquid is not going completely dry this time. And what is the amount? It is 1.62763 by 2, which is around 0.8138. Okay, nearly 81.38%, and that information matches with our observation in the PT envelope curve. So in today's lecture, we have performed 4 practice problems of miscellaneous in nature, and we also have done a couple of case studies. So with this, we end our lecture today. We will continue in the next lecture. Thank you.